Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog.
Good evening. I'm Yvonne Stapp for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations. Tonight, we are honored to talk for the second time this year with Priyamvada Natarajan, professor of both astronomy and physics at Yale University. This time, we discuss how scientists in this field really unravel the mysteries of the universe. In addition to her academic position as a theoretical astrophysicist at Yale, Dr. Natarajan also holds the Sophie and Tycho Brahe Professorship of the Dark Cosmology Center at the Niels Bohr Institute in the University of Copenhagen, Denmark. She also holds an honorary professorship for life at the University of Delhi, India, and Dr. Natarajan is also an elected fellow of the American Physical Society. Her list of distinctions is very long, so we refer you to her website or to tonight's event page on our website for more information. The focus of Dr. Natarajan's research is in dark matter maps of galaxy clusters, among other major concerns of astrophysics. But she is also very committed to communicating science to the general public. This commitment is reflected in her articles in New York Review of Books, and most especially in her splendid book, Mapping the Heavens: The Radical Scientific Ideas That Reveal the Cosmos. We are delighted for the opportunity to talk to Dr. Natarajan about how she and other scientists actually make their discoveries and about the importance of public science literacy today. We're very pleased to welcome her tonight. Welcome, Dr. Natarajan.
Thank you so much. It's such a pleasure and a privilege to be back here again talking to you.
Thank you. And I wonder if we could start off, we were concerned with the knowns and the unknowns and how your field resolves these big mysteries, probably some of the biggest. And so I wonder if you could tell us something about a few knowns in astrophysics and then maybe a few unknowns. Go ahead.
So I think one of the exciting things about all science, and of course about astrophysics as well, is that we are constantly pushing the boundary between what is known and what is unknown. And that's really what research is all about, trying to sort of enlarge the domain of what we understand reliably with evidence, with data. So for example, in cosmology at the moment, one of the things that we understand extremely well about the universe is the life cycle of stars. We know how stars form, we know how they evolve and age and how they die, and we know as a function of the initial mass of a star, how massive it is to start with, how it would evolve. So all these tracks. So that physics is extremely well understood, for example, right? However, there are lots of concepts that are not as well understood. And one particular example is the idea of dark matter. And the idea of dark matter today is very much unlike sort of the invisible fluids and invisible entities of the past, like even ether that went away. And the reason that this is a different concept, this is here to stay, although we don't know a lot about dark matter, we do know that the bulk of the matter in the universe is made up of this dark matter, which does not emit, absorb, or reflect light. But it has mass. It's some exotic particle that formed in the early universe. We don't know which particle it is. We have some candidates. We haven't found it. However, because dark matter has mass and it exerts gravity, you see the gravitational influence that dark matter exists everywhere in the cosmos. So dark matter is sort of very lightly smeared pretty much everywhere in the universe, but it lumps in certain places. And because it lumps, and according to Einstein's theory of general relativity, it deflects light. So we can infer the presence of matter by the light deflections that it causes. And so that's detected. And so we can make these very, very accurate maps of dark matter, very sort of detailed maps of dark matter, even though we don't know what the dark matter is. So I think it illustrates very, very nicely this sort of boundary between what is known. So aspects are extremely well known, and its existence, there's incontrovertible evidence, I would say. I mean, there's some skeptics within the community who are trying to look for alternative theories. I mean, and this is part of science, right? Nothing successful yet as a viable alternative. But, you know, we're constantly pushing, and the boundary now is obviously to try and find and pin down the particle. And either pin it down a bunch of different ways. Pin it down by directly detecting it, using either the Large Hadron Collider in CERN or direct detection experiments that have been devised, sort of focused on the expectations of the kind of particle that we think constitutes the dark matter. So far we had been fixated on this particle called the neutralino. But, you know, we've come up empty so far, looking for this particle. Another viable candidate is the axion, and till very recently we believed that the axions were possibly a little too light to really be to account for all the dark matter, plus for us to detect. But it turns out we've had a new breakthrough at the moment, and there's been a recent recalculation, and it's possible to have a slightly heavier axion with slightly different properties. So, you know, you can expand our search space now. And so the other way to finding sort of a dark matter is sort of indirect ways from astrophysics, like the sort of work that I do, which is coming at it by looking at sort of more collective phenomena, sort of looking at, you know, aggregates of dark matter particles, how they behave, and then try to sort of zoom in on what kinds of candidates might be permitted or not. So I think this sort of illustrates, you know, the case of dark matter really, you know, brings into sharper focus the fact that there is this ever-moving boundary of between known and unknown. And the project of research is to really push at this boundary.
Okay. Just on that very, very quickly, there are things like multiverses and so on that seem much more speculative, whereas this, it sounds as though originally maybe it was treated almost as a bizarre idea originally, but increasingly there's less and less doubt about it. It's a question of time until they identify, and that's one thing. And there are others that seem to be very unknown, very unknown.
So the interesting thing about dark matter is that the discovery of dark matter actually came from data. So it wasn't a theoretical idea that was proposed. It was actually came completely from empirical data. And so there was a need for some kind of unseen matter that would basically hold up galaxies and account for the gravitational influence they have on the motions of stars in them and so on. The concept of the multiverse is slightly different. It's a theoretical idea, and its origin comes from the fact that, you know, in order to describe almost all the properties of our universe, you just need a handful of numbers, which can be measured. And we have measurements for our universe for those numbers, and they have very specific values. And the question is, if these values were even slightly different, we would not end up with the universe that we have. We wouldn't be here to ask those questions and so on. So the idea then is who or what, more interestingly, what determines what those values are for those parameters, defining parameters. And an easy way out, I'm not saying that it's a cop-out, but an easy epistemic way out is to say that you have these 6 numbers. They have distributions of potential values, and, you know, various combinations of 6 are actualized in different universes. So there's a multiplicity of universes out there. We just happen to be living in one which has the values that we measure. And so potentially you could have an infinite number of universes. It is a speculative idea, and at the moment we haven't quite figured out how to test the idea. I mean, there are some interesting potential lines of inquiry, like, you know, maybe you could have some kind of remnant from early collisions of 2 bubble universes that are part of this infinite multiverse, and maybe there would be some kind of imprint on our universe, perhaps on the cosmic microwave background radiation, which is sort of the relic radiation from the Big Bang, something like that. You know, I sort of comfort myself when I think about this. You know, in 1543, Copernicus, right, shifted the pivot from the Earth to the Sun for our solar system, right? He could have never even imagined that human beings that we would have been able to launch 2 satellites, the Voyagers 1 and 2, that could actually leave the entire solar system. At his time in 1543, the solar system was the cosmos. We didn't really know about anything else, right? So he could have never imagined that we had the cognitive capability to figure all of this out and actually send off these 2 spaceships outside, satellites, out to the edges of the solar system. Actually, they've crossed the solar system now.
Yeah.
So, I don't know what one can't predict what future science might reveal to us. I remain very optimistic that, we might actually find a way to empirically test the idea of multiverses.
Yeah.
I don't know when, but I have no doubt that, we potentially could.
Right, but it's a very good point that it's unknown. Well, we don't have a way to prove or disprove at this moment. Another one that was a little less controversial for a very long time was the Big Bang itself.
Yeah.
Is that now a known?
Oh, absolutely.
Okay, so
there's incontrovertible evidence for the sort of the fiery, sort of fireball beginning of the universe, that the universe started from a very hot, dense, compact state that is extremely well established by many, many independent lines of observation. There are details that we still could understand better, but I think the sequence of events is extremely well understood.
Okay, so you've made tremendous progress in actually confirming things that had to be speculative because you didn't have an option for a very long time, and now you have more like degrees of certainty in some areas, and you're clear about what things are speculative for the time being, but with technology improving so much, so fast, and so on. That we're doing really well. I'd like to talk about a wonderful article that you wrote in the New York Review of Books. It's one of my favorite all-time articles, period. And you reviewed several books in that one. And the thing that I found most interesting was one dealt with curiosity, one dealt with ignorance, these are books, and one dealt with the blunders that scientists make, and these people are very prominent scientists and writers. In any case, you made a very big point of the provisionality of science. Could you please trot us through that?
Yeah, so I think that was my first essay for the New York Review of Books, and I had a tremendous amount of fun writing it. So I think the main point that I really wanted to put across in that essay was the fact that there are fundamental features of science which actually give vitality to the subject, which are essential to the nature of science and the scientific enterprise. And these concepts are the ones that drive scientists to do their work. However, these are the very concepts that make it very difficult for the public at large to understand science, to comprehend it, and also to really get a feel for how science progresses. And so I think key to that is the provisionality of science. This notion that anything that we know, this boundary between the known and the unknown, the ever-shifting boundary, that provisionality, that what we know today is the best to date knowledge, best to date understanding, and that when we get better data, more sophisticated instruments to make better measurements, then our understanding is going to get honed and it is going to change. So scientists are actually very excited at this prospect of change and evolution. And I think the public finds it a little disorienting because the pace of scientific discovery is so high today, the pace is so fast today that it's very hard to keep track of what's going on, and it's hard not to feel sort of disoriented by the process, by the sort of the new discoveries that are sort of coming apace. So I think there's the provisionality of science is one concept, and then hand in hand with that is the idea of uncertainty. The fact that measurements have a fundamental uncertainty that comes from the limitations of the instruments that we have to make them. And they also come from the limitation comes also from our understanding at a given point. So once our understanding improves, the data improve, we have a much better view, a much better theoretical grasp of the concept, and this is how science really progresses. And that, these are, I think, facets of science that are particularly exciting for scientists. And as part of our training, we are taught to stay open-minded. And so it really, at the bottom of this is how to remain open to change. And how to remain nimble so that you can change your mind when new evidence suggests that you have to change your mind.
And that's part of the discipline, because scientists are as guilty as anybody else for having
Absolutely.
a bias.
Yeah.
They can't help it.
And I think that in my recent book, I really talk about this. I talk about even the fact that we are humans after all. Scientists are human. And despite our training, even we resist new ideas when they're first proposed.
Yes.
And particularly if they're somewhat radical. If they're not, they're radical in a real departure from whatever is the conventional thinking at that moment. So even scientists push back. But eventually scientists, partly because they're training and partly because they are open-minded. And the data evidence really dictates how we change our mind. And we are forced to change our mind.
In terms of scientists enjoy this,
Absolutely.
the unknown and surprises and everything else, and you're trained for it to a certain extent, but it seems to be a mentality to begin with, a curiosity that is kind of insatiable and flexible for the most part. It is really critical that we in the public become more like this, have a more open mind. But for centuries, the traditions have ruled us. So whatever the tradition of our particular cultures, the religions or the politics or whatever, that's handed down, and it's very firm and it's very authoritative. Do you think we can overcome this, that the public
Absolutely. I mean, I think that, there is no reason that even someone who is not trained as a scientist cannot be flexible, open-minded, and nimble in how they think. And I think you were absolutely spot on when you said that part of that has to be an acknowledgement and respect given to curiosity and wonderment and questioning. The fact that, you have to be open to not just asking questions, but also be allowed to ask them and want to ask them and want to challenge them. That is a sort of very active engagement with ideas at all times. I think that part of the sort of institutional, sort of top-down handing down of ideas is underlying that is the notion that some things cannot be questioned. And you cannot engage with them. So that's a very passive stance of dealing with the world. We can no longer have that. The world is changing really fast. We are changing it, together. All of us around the globe are changing it. And I think, therefore, we have to be able to be open to challenging what's going on and thinking critically and asking probing questions about what's going on so that we can understand. So actually there is a biologist, John Miller, who I think has a very nice idea. It's called civic scientific literacy. And he talks about this concept of how to live in a democracy. The citizenry have to be aware, they have to be questioning, they have to be engaged so that they can actually participate much more effectively as citizens in the country, in the world, on the globe, but also in their personal spheres when they take decisions. You take a decision about medical treatments that you have to take. If there's a chance of, there's a probability that if you go through radiation therapy, then the cancer that you have has, a certain probability of being gotten rid of. You have to be able to make those judgments. And I think we live in a complex enough society now that we all have to make these judgments all the time. And so being better equipped with the means, with the mentality and the means. So the mentality to be curious and ask questions, and the mentality to be actively engaged. I think you need the combination of both. And this sort of scientific temperament is what it was classically called. I think it's much needed in today's world.
And much more broadly.
Yeah.
You bring up a very good point there, that you really, in a sense, you cannot separate the civic literacy from the science literacy. Not today.
Yeah.
This is global. It's diverse. And it's
all
constantly
pervasive.
changing.
I
all
think
pervasive.
Science and technology are so pervasive in our lives now that we actually cannot function as a people anywhere in the world without science and technology.
Right, and if we're going to save the world, we most certainly need to have this attitude. And it's curious, children have that curiosity. It somehow gets drummed out of us, it seems like, but it's cheering to think that, scientists maybe it will be contagious. That's what we need, a contagion, a different thing.
And, and this sort of element of surprise.
Yes.
Being the ability to be surprised.
Yes.
And you actually have to be open to being surprised.
Exactly.
And in science, because a lot of the discoveries have a serendipitous element to them, that once again, we are open and trained to accept serendipity when we encounter it.
In terms of your own work, you obviously have a very broad mind and so on, but you must have come up against some real challenges in your spectacular discoveries. Could you tell us, give us an example of your own experience with this, unknowns and...
Yeah, so I think that my own experience, sort of one of the interesting intellectual challenges for me has really been about the practice of science, about how science is now done. Science now, especially in my field, is done in large collaborations, in big groups. And so that, because the field is mature, the questions are complicated, and you need the gifts of many different kinds of people to work together, to cooperate and tackle a scientific question. For me, one of the challenges has been that, I would like to retain creative freedom and intellectual freedom. And part of belonging to collaborations is there's an element of doing science by consensus. And I actually want to be able to take creative risks, the kind of risks only an individual can take or a small group of people working together on a speculative idea can take. And so for me, the conflict, if you will, through my career so far has been, there's a part of me that wants to be included in the sort of big enterprise, big science. And then there's the other part of me, which is really the more sort of true part of me, the authentic part of me that wants to work on my own. Not entirely solitarily, but in smaller groups. So I think the tension for me has been the desire to push, to do speculative stuff, not all the time, but to be able to push on the speculative boundaries of the knowns and unknowns. Take the risks of known and the unknowns, and to synthesize and use ideas that you have learned in some other sphere, kind of reapply them sort of to new questions, to have the freedom to do all of that. So I think for me that has been a bit of a challenge. But what is lovely about the scientific community is that the community itself is very open to all kinds of styles. It's really the funding where these things sort of come into sharper focus, That because it's big science needs big money, that's really the model that's funded. And that's really where a lot of the funding goes. And individual researchers and small groups are not as well funded, in the last decade or so. I'm hoping that, it'll change in the coming years.
If we have the public awareness, I think that would change. That needs to be publicly funded. People need to understand that you must fund long-term, some of it's speculative research and so on, but there's plenty of money. It's just going in the wrong directions, it's being wasted. But thank you for sharing that with us. I guess that might be I don't know, a common attitude among theoretical people anyway. They're back of the envelope and they need to speculate and they need to take risks.
I just think that there's room for all styles.
There is, yes,
there is room for all styles
and it's
all
important
types.
as history, as you have shown in your book over and over, that people started out and they were very unpopular with these ideas originally, over and over in your field, certainly, where many of those ideas were not just unknown, stones, but they
Right.
would look like they were off the wall, originally. So it is changing. But thank you for bringing out that we all need to adjust our mentality here, and that if we did, it will be much more exciting anyway.
Yeah.
I have one more thing to ask you about,
Absolutely.
if you would. You are, as a member, you do work with something called the EDGE. Jon Brockman, I don't know if it's a familiar name for people, it's a very interesting .org. You have done work with this, and you are cited by Brockman. Could you tell us about that? One of the things, well, I've asked you.
Yeah, no,
about-
I think, Jon Brockman is an incredibly interesting mind. You could call him sort of an evangelist for science, and for a sort of a new kind of science, a more integrative approach to science, combining science and arts. And, there was a sort of this infamous sort of false dichotomy sort of between science and the humanities, science and the arts, attributed to C.P. Snow, the two cultures. And I think Jon Brockman started this new third culture where he believes that you can actually unify. And I'm in complete agreement with him, because I think that there is no way that you can actually separate out these ideas you can't parse big ideas into science and arts and humanities. I think these disciplinary boundaries are quite artificial, and they actually prevent us from making leaps in progress. And so it's a wonderful organization where he invites people who are thinking and working on a whole bunch of different fields, scientists, humanists, and he provides them this interesting platform. It's a nice long interview about why they do what they do, how they do, and invariably listening to anyone, any one of those, you would immediately see that these sort of artificial disciplinary boundaries really don't hold the excited curious intellectual minds behind it all. I mean, they really don't kind of believe in these boundaries. Most of us are transcend these boundaries in how we work, in how we think, and who we are.
And I should mention that you write poetry, and you are very comfortable in the arts. And I see this constantly with people in science. They don't see these barriers. These have been artificially imposed, as you say, a kind of tribalism, an artificial tribalism.
And possibly, an artifact of, academic departments and universities, and how we organize intellectual work. And I think that, I think those boundaries are going to dissolve in time. And it's definitely true that a lot of the most exciting, cutting-edge work today is happening at the boundaries.
Very interesting. Very interesting that people...
The intersections of those boundaries.
What is, before we leave, what is like your current project that we should...
The current exciting project that we just finished a couple of papers in my research group is on, so one of the problems I work on is the origin of the first black holes in the universe.
Yes, that's right.
And so the traditional idea was that the first black holes, the seeds that you would get would be from the end states of the first stars that formed in the universe. So they would burn up all their fluid, they would burn up all their fuel, and then leave behind a little remnant black hole. And that would be the seed from which all the supermassive black holes that we see today in the centers of most galaxies, including our own, that's how they would have originated. But the idea that this may not be the only way to make the first black holes was something that we came up with about 10 years ago. And that was driven by the fact that growing black holes are seen in the early universe as quasars. So the gas that is falling into the black hole, as it makes its way into the black hole, glows in the X-rays or in the optical. So it's very bright, and it outshines the entire galaxy. And it turns out that we're finding these bright beacons earlier and earlier in the universe, and they're brighter. They're extremely brighter and brighter as you go back. And this is very peculiar. That suggests that they are powered by more massive, supermassive black holes than we imagined earlier. So then that brings us to a bit of a timing crunch. So you form the first stars, you have the little remnant black holes, and then you are immediately seeing, very soon after, 500 million years or so after the Big Bang, you are seeing these black holes that are about 1 billion times the mass of the sun. that are glowing because of the gas that's falling into them as quasars that we're detecting. And we're starting to see a population of them. So if you need to grow a seed from 10 times the mass of the sun to 1 billion times, we have very little time available.
Yeah.
And so we came up with this idea of direct collapse black holes. So these are black holes that are much more massive from the get-go when they form. So this is a black hole that forms that's about 10,000, 100,000 times the mass of the sun. And it forms bypassing the formation of a star.
I was going to say.
So you have a gas, you know, in the early universe, you have this gas disk that gets unstable and starts siphoning the gas to the center, and you bypass the formation of a first star. So it's rather like, you know, if you have a bathtub and you unplug the bathtub and the water starts to, you know, fall in very rapidly, you see that little vortex?
Yes.
It's the same kind of phenomenon with gas, and you accumulate matter very quickly to the center, and you would form this direct collapse black hole. So the interesting thing, of course, is how would we know? When you look at a black hole later on, for example, we look at the black hole at the center of the Milky Way, which is about, you know, 1 million times, 4 million times the mass of the sun. You cannot tell how this black hole formed.
I see.
Right. So there's no memory of how the black hole actually, what went into the black hole.
No trace.
No trace at all. And that's a feature of black holes, that we don't actually know how they, what all went into forming the black hole. So what we discovered, though, is that these direct collapse black holes go through a very interesting stage in the early universe. They form and then they rapidly merge with a galaxy that has formed stars instead of forming a direct collapse black hole. And there is a stage when the mass of the black hole and the growth of the black hole will outshine all the stars. And so they'll be very, very bright objects, but in the early universe they'd be very dusty. So you would see them not in the optical or the X-ray. The X-ray penetrates through dust, but this is a huge amount of dust in the early universe. So where you would see them is in the infrared, when you would have the radiation that's sort of absorbed and re-radiated in the infrared. So this is sort of long wavelength, low energy. And so the James Webb Space Telescope that is going to be launched in 2 years actually has the best detectors to date in the infrared. The near infrared, the mid infrared, and the far infrared. So we just predicted the spectral signatures, the fingerprints of these objects, and we discovered that James Webb Space Telescope should see them if they're there. They're booming. They would be bright in the infrared. And so they should be detected if they're there. And you know, if we are right and this model is right, they should be detected. So that's what's the most exciting thing. It's literally hot off the press. We just submitted the paper and we're working on we got referees' responses.
And you can't wait for that telescope to
I can't wait for the telescope to go up. Absolutely. It will be so exciting to have.
Yes. Well, that's a brilliant example of exactly what we've been talking about. You have an unknown, you speculate, you get as much evidence as you can, but then you're waiting for a technology necessarily to confirm it.
Right, you make a prediction. You make a prediction, and it's either going to be validated or not, and it's exciting either way. Right, we'll learn something either way.
Right,
you know?
But it's also revolutionary in terms of the thinking of black holes at the beginning. So you'll be getting a Nobel Prize. I'm so glad you came to see us before then.
I don't know about that, but you know, I'd just be thrilled. I mean, I think for me, what is really exciting is to be doing science right now, where you know the first sort of proposals for this idea we put forth in 2006 in papers. And can you imagine within 15 years years of your lifetime, the idea can be validated or invalidated.
Yes,
I mean, I think that this pace and the fact that you know it happens in a lifetime. And that I feel very fortunate and lucky to be here and to be able to do what I'm doing. I still can't believe I'm paid to do this, right? So,
but the field is very fortunate to have you too. And thank you ever so much. You've really given us a good earful here.
Okay, great.
A lot
thank
of
you
good
so
things
much.
To think about. We will stay tuned for this. I think everybody in the world is waiting for the James Webb to go up. There are so many things that are going to be
open a
determined
new window
when that goes up.
Universe,
So that's going to be a great revolution by itself. Thank you so very much for being with us.
Thank you so much for having me.
Pleasure.
Yeah, it's a
great
real
pleasure
to talk to you
and the best of luck to you.
Thank you.